Hey kids, it's time for trigonometry. Section 5.2, angles in all the quadrants. Okay, so the big thing here today is learning about this thing called a reference angle. The reference angle is the angle between the terminal arm and the x-axis. So what we were doing before is we were measuring all of our angles from the positive x-axis and going in generally a counterclockwise direction for a positive angle. Now we're saying the reference angle is this angle between the x-axis, and it's not always just the positive, it could be the negative x-axis as well. In fact, it's just whichever one's the closer. So what we do is we use the reference angle for calculating sine, cosine, and tangent if we have an angle bigger than 90 degrees. So an angle like this one up here might look like, let's say, 120 degrees, but the reference angle is this guy right in here, which is 60 degrees. So when we're calculating sine of 120, we're actually going to use 60 degrees in the calculation. That's what calculators do as well. So one thing we can say, for example, sine 30 and sine 150 are the same because they have the same reference angle. Now, if you're not 100% believing me, look at what I have. I have this digital calculator, which is pretty nifty. It's the TI-83 Plus. I'm going to move my face over here for today so I can have the calculator here. Okay, so we can actually use this thing, and we can type in stuff. And of course, it's gone ahead and froze on me, which it does from time to time if I don't use it enough. So I guess I'm just going to have to go and I'm going to have to open it back up again. Okay, so desktop, and then we'll go to my virtual TI. Okay, so hopefully it's working this time. There we go. Okay. Anyway, never better than the real thing, but it'll work. So sine of 30 degrees, we can type in sine of 30, we can push equals. Uh-oh, that's weird. Now, if you're really paying attention, you'll notice that's not the right answer. You always want to make sure your calculator is in degree mode. Okay, so let's try that again. Let's go sine of 30 degrees. We'll push equals. There we go, that's 0.5. That makes more sense because as we learned from the special triangles, sine of 30 is actually 1 over 2. Calculators won't give you 1 over 2. They'll give you the, okay, hold on. Yeah, you can't actually do that, by the way. You gotta, yeah, type in sine. Okay, sine of 150. Anyway, there we go. Okay, so that was a little harder than I thought it would be, but we got there eventually. Sine of 30 is 0.5, sine of 150 is 0.5. They share the same reference angle, because when you're doing a 150-degree angle, which might be like that, there's 150. Well, the reference, okay, well, there we go. The reference angle here would be 30. And the two always have to add up to 180, if that's not obvious. Okay, so what would be a useful thing is if we actually just did this, draw 4 angles in standard position that have a reference angle of 30 degrees. So another thing I can do is I can just say you have a reference angle of 30 degrees, but that means you could be in quadrant 1 with a reference angle of 30 degrees, but you could also be in quadrant 2 with a reference angle of 30 degrees. And what that's going to do for you is it's going to put you over here in quadrant 2, and you're always going away from the x-axis. But you could also go below the x-axis. So maybe in a different color, I'll pick green. You could go below the x-axis and you could have a reference angle down here of 30 degrees. And you could even have one in quadrant 4. We'll go with purple, I guess is the only color I haven't done here. We'll go with purple and we'll draw that going out there. And that is also 30 degrees, okay? So there's 4 possible angles that all have the same reference angle, and one belongs in each quadrant. So what we're going to do is we're going to use a calculator here, and we're going to figure out, if I can just find my little, there we go. We're going to figure out what the values of sine, cosine, and tangent are for 30 degrees. This full angle going around here is 150. Going even further, spinning around here, that is 210, and I remember this is 180, right? So 180 plus 30 is 210, and then the last angle here, we're spinning all the way around, and and we're going to go 360, but we're backing up 30 degrees, so that's going to be 330. So if you go to a calculator and you type all this in, and let's see if I can get that calculator back. Okay, so we know what sine of 30 is already, so we don't need to work that out. It's 0.5. And I think it's, my calculator's going to hide it on me, okay. And then we can go to cosine of 30. We can push equals, okay. And we'll also just do tan of 30 while we're here. Oops, come on, let's not do that. Okay, so 0.866 and 0.577, so this will be 0.866 and this will be 0.577. And if you go through and you do all the other calculations, and I'm not necessarily going to do all of them because we're going to see a pattern emerge pretty quickly. Okay, so we're going to do sine of 150, and that's equal to 0.5, and then I'm going to go to sine of 210, and that's equal to negative 0.5. Okay, so that's a little bit different. And then we're going to go sine of 330, and we're going to get negative 0.5. So let's just write all those values in. So this is positive, but this one was negative, and so was this one. What's going to happen for cosine here? So we're going to go to cosine, and we're going to go cosine of 150. Now, this is where you might take a sec. You might even pause the video and just think, what is this going to equal? This is a good way to test yourself. When I push that, I get negative 0.866. That's interesting. Okay, we'll explain why that is in just a bit, but let's just get the other values. Here's 210, also negative 0.66, and if we do this, we get back to positive. So in this case, for cosine, we actually have negative here, and we have positive here. Finally, for tan, tan of 150, tan of 210, and tan of 330. So negative, positive, negative. So this is negative. We can see these are all the same value because they share the same reference angle, but the sign is what I really wanted to illustrate here. Okay, so what we can see is, let me just highlight the positives. Sine, cosine, and tangent are always positive here in quadrant 1. But in quadrant 2, only sine is positive, whereas cos and tan are negative. In quadrant 3, sine and cosine are negative, only tan is positive, and in quadrant 4, only cosine is positive. So what is the explanation for why that happens? It's not just some random magical thing in math, there's an actual good reason for that. So what we can do is we can take a second just to explain these signs. So the sign of each ratio depends on whether the opposite, adjacent, and hypotenuses are positive, negative, or 0. So one thing we'll say is the hypotenuse is always positive. So the length of this terminal arm here, that's always positive, okay? And if you'd like some proof of why that is, remember the distance from the origin is given by this equation here. This is always positive, okay? It's the result of Pythagoras. The adjacent and opposite sides are positive only if the x, y values are positive. So what that means is if we draw a triangle in the quadrant 1, we have a positive x and we have a positive y. But if we draw a similar triangle over here in quadrant 2, we've got a positive hypotenuse and a positive y, or a positive opposite, but the adjacent side is negative because the x is going to the left, the y is going up. Same thing with some other quadrants here. If we did it in quadrant 3, we'd actually have a negative and a positive, and so on. That's going to clutter up my diagram too much, so I'm just going to erase that. That's what's going on here. So for example, in quadrant 2, only sine is positive because that's the combination here of opposite and hypotenuse, that when you divide a positive opposite by a positive hypotenuse, you get a positive value. Cosine, which would be adjacent over hypotenuse, would be negative because it's negative and positive. And tan, same thing, positive over negative. So sine is positive in quadrant 2 simply because it's the ratio of the two sides that are positive. Okay, there's a way to remember all of this. All students take calculus. So what you can do if you'd like a simple type here, A, S, T, C. So starting in quadrant 1, so that in quadrant 1, all the trig ratios are positive. All trig are positive. In quadrant 2, only sine is positive. In quadrant 3, only tan is positive. And in quadrant 4, only cosine is positive. And you might take a second just think about why is that the case. In quadrant 3, tan will have a negative adjacent, it'll have a negative opposite and a positive hypotenuse, but negative over negative is positive, so it'll be positive. Same with cosine. Okay, so let's do a little example. Points located at blah, 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 determine the reference angle of the terminal arm. So if we actually drew a little sketch here, and I always need to sketch this, and you should too. -1, comma, root 3. So just, by the way, that's approximately 1.7. Just happened. Okay, so let's just do a little sketch here. -1, comma, root 3 is going to be somewhere up there, and the terminal arm is going to then look like this. Now, if you're wondering where the heck did root 3 come from, this is because this was chosen specifically to have some special angles, kind of a thing going on here. So how do we figure out the reference angle of the terminal arms? The reference angle is this guy in here. Let me just change color. It's this guy right in there, okay? So that is theta ref. So the reference angle is in there. So what we're going to do is we're going to zoom in and we're going to say, so this is like a zoomed in view. And we're going to say what we have is we've got this situation going on. Okay, the origin's over here. Who cares about the origin? Whatever. It's this point right here. So this is at -1, comma, root 3. If we want to figure out the reference angle, then what we do is we call the adjacent side, we give it a length of -1. And we give the opposite side, which is the y, 3. Now, here's the thing that's a little bit sneaky about this. If you are a special triangles champion, and you should be, but if you're still working on it, that's fine. 1, root 3, 2, this is your 60, this is your 30. If you have this memorized, because it is one of those ones you need to have memorized, great. You can do this one of two ways. Method 1, using special triangles, we can say the reference angle equals 60. There's no work to show for that, you just know. But 2 is you can use the calculator. Now I wanted to show you this just simply because if you're going to figure out that reference angle, you're going to have to go inverse tan, but what you type in, and this is really, really, really important, you don't type in root 3 over -1. You're going to type in root 3 over +1. Your calculator will get confused if you put in a negative sign. So let's put a big note here. When using the calculator for reference angle calculations, always, always, always use positive lengths for the sides. That's really, really, really important, because if you don't, you're going to get something funny a lot of the time. So let's actually just do this. Let's go second function, tan, and did my calculator just give up on me? Yeah, it did. Okay, so this is kind of buggy, which is why it's also not my favorite. But let's just have a quick little look here. Psi. Okay, let's just open it up one more time, and if it starts bugging out on me too much, I'll just stop using it. But what we should be able to see is if we go, change it to degree every time, what we should be able to see is if we go second tan, and we go root 3, I don't need to go root 3 over 1, I can just do root 3, that's fine. Close that all up. I should get 60 degrees. If I did second tan, and I put in negative root 3, let's see what happens. And then I get negative 60, and that's where it can get kind of confusing. Once you start to really understand what's going on in your calculator's brain, it sort of makes sense, but it's actually not that obvious. I don't necessarily know if a big explanation is gonna be super helpful right now. So what I'm going to say is stay away from putting in negatives when using calculators. Just go ahead and do the positive side lengths. Okay, so this is going to give us a number of 60. This also explains why using special triangles is a little bit safer. Okay, finally, how do we figure out the angle in standard position? This is actually really easy. Now, there's formulas for this, or you could use common sense. In quadrant 2, our angle in standard position, we can calculate that by going 180 degrees minus the reference angle. So what we're doing is we're going all the way over to 180, and then we're backing up 60. So the angle, of course, is going to be 120 degrees in the reference, in standard position. In case you're curious, are there other similar formulas for the other quadrants? Yes, this is just an FYI. This is not the problem, but in quadrant 3, theta would be 180 plus the reference angle, and in quadrant 4, it would be, you're actually going to go 360 minus the reference angle. In quadrant 1, the reference angle is just the standard angle, same thing. Okay, anyway, this is the answer. Box that up. Send it away. Okay, the value of sine, cosine, and tan. So what we have is we have this angle here. We're in quadrant 2, and we know we've got 120 degrees here, and we know the sides of the triangle are -1, √3, and of course the hypotenuse is 2. So what we would say is we would say sine of theta. We know it's 120, but we don't really care. That will be equal to opposite over hypotenuse. Now when you're doing this, it actually does make sense to keep the negative signs in. So the opposite side is √3 and the hypotenuse is 2. And we're going to leave it like that because it's positive √3 over 2. Done. Cosine is adjacent over hypotenuse, so it will be -1 over 2. And tan is √3 over -1. If you actually leave it in like this, you're going to naturally get cosine is negative and tan is negative, and of course sine is positive. And that's exactly what the mnemonic, all students take calculus, because we're in quadrant 2, we would expect only sine to be positive. Cool beans. Okay, here's one more. For an angle in standard position, cosine theta is equal to -1 over 2. Which quadrants could the terminal point be located in? So what we're told here is cosine is negative. So what this says to us, all students take calculus. In quadrants 1 and 2, cosine will be positive, but in quadrants 3 and 4, cosine is negative. So what we can say is cosine is negative in quadrants 2 and quadrants 3. If it bothers you that I keep switching between Roman numerals and normal numbers, good. Okay, what are the possible angles if theta is somewhere between 0 and 360 degrees? We have to say this, by the way, because if I don't give you a limit, you could keep spinning around and around and around and around forever, and you could go up to like 10,000 degrees. So we're actually just sort of limiting to one full rotation. And we're not allowing negative directions either. Not yet. Hey, what do you think the next lesson is going to be on? Okay, so what we could say is in quadrant 2, we could say that theta is equal to, remember, it's going to be 180 minus the reference angle, and in quadrant 3, we could say that it would be theta is 180 plus the reference angle. Rats, we don't know the reference angle. Can we work it out? So what we would do is we'd sit here and go, is this a special angle? And I think it is, because what we have is we have up here, we have information about the adjacent and hypotenuse. So if we have this sort of situation, 1, 2, √3, and we have the adjacent and the hypotenuse, right, because cosine is the adjacent and the hypotenuse, we know that this angle in here is, hey, test yourself, this is 60. I always get 60 and 30 confused, but 60 is the bigger angle, which opens up to the bigger side, so you can remember it that way. Anyway, the reference angle is actually going to be 60. So what this tells us is it should be 180 minus 60 gives us 120 degrees as one of the answers. The other one would be 180 plus 60 to give us 240. So what we just did is we just figured out that if you pushed cosine of 120, we should get negative 1/2. And if you push cosine of 240, we should also get negative 1/2. Let us just take a sec. I'm going to go ahead and guess that. Yeah, okay, I'll crash one more time. All right, well, as much as I hate doing this, I'm just going to do it one more time because I think it's actually worth seeing. So we're just going to jump over here and we are going to grab that and just show it one more time. I think, if I had to guess, I think my calculator doesn't like when I don't have it in my screen. It gets upset with me. Okay, so let's actually just type in cosine of 120. Is that equal to negative 1/2? Ba-da-da-ba. And then cosine of 240, same thing. Okay, so we just figured out the angles without needing a calculator. So that's actually pretty cool. And that's it. So the black screen of doneness says that's all for today, folks.